All right, we're going to have a pretty abrupt change of gear here in class where we've gotten out of talking about experimental design and we're going to get back into kind of hardcore aqueous chemistry and look at how we can use specific aspects of chemical equilibrium to solve a variety of environmentally and biologically relevant analytical problems. So our first order of business is we're going to, having taken a day and a bit to review some of the fundamentals of kind of second and third quarter Gen Chem treatment of equilibrium systems, we're now going to look at equilibrium chemistry problems in a lot more detail and talk about some specific aspects of equilibrium like ionic strength effects and coupled equilibria that are necessary for solving chemical problems in real world systems, and look at how we can take a systematic approach to solving any equilibrium problem by considering all the related equilibria and specific statements of stoichiometry within chemical equilibria like charge balance and mass balance to effectively solve quite complex equilibrium problems. And the fundamental reason for getting into this systematic treatment of equilibria is that equilibrium reactions define most of the environmentally and biologically relevant chemical reactions you'll encounter. So chemical equilibria can quickly explain why, for instance, in an eastern United States river, you might have a 10-mile dead zone where no fish live because of industrial pollution, but the addition of a paper mill farther down the river restores the pH of the water, and fish and most aquatic wildlife live normally just past this dead zone. A series of coupled equilibria discussing how bicarbonate interacts with the acidic mine waste dumped farther up the river to neutralize it and restore the pH balance of the river relies on a discussion of equilibrium. And before the close of this module, this is a problem that we'll look at. It also explains why we can't count on happenstance to solve environmentally related chemical problems, because the same type of equilibrium involving bicarbonate, carbonate, and dissolved carbon dioxide in water can also be a huge driving force in coral reef die-offs, impacting ecotourism and conservation, and why increasing dissolved levels of CO2 in water are a significant contribution to the death of coral reefs around the world. Chemical equilibria is at the heart of all these problems. And we need to build a robust tool set to solve problems where we have to consider more than one related chemical equilibrium in a series to solve a problem. And we also have to be able to explain phenomena like why the position of an equilibrium appears to be shifted, not simply through Le Chatelier's principle, but by changing the overall amount of dissolved ions in a chemical reaction. So for instance, this is a chemical equilibrium that you likely encountered in general chemistry, where a mole of iron 3+ reacts with a mole of the polyatomic anion thiocyanate to form in equilibrium an iron thiocyanate complex with a bright red color. While the equilibrium constant is indeed a constant for this reaction at room temperature, depending on the amount of potassium nitrate you dissolve in the solution, you can actually shift the position of this equilibrium and change the ratio of the product to the reactants without actually changing the value of the equilibrium constant. Why is this? Well, it turns out that the presence of ions impacts what we call the ionic strength of the solution. And the other ions in solution can interact with the dissolved ions that are reactants on the left-hand side of the equation and make it harder for the two players in this reaction to interact and form bonds. This is what's known as an ionic strength effect. Even though neither potassium, K+, or nitrate, NO3-, is involved in the equilibrium shown here, the presence of other ions can actually influence to what extent the iron thiocyanate product forms in solution, which by eye is indicated how red this solution gets. And so to really deal with equilibrium problems that take place in the real world, we have to be aware of not only when we have interrelated equilibria that pull on each other through Le Chatelier's principle, and how we solve problems related to multiple equilibria to describe a chemical phenomenon, but we also have to take into account the phenomenon of the ionic atmosphere and how the interaction of other ions in solution can influence the progress of an equilibrium reaction, even though they don't take part in the reaction directly. And these two skills, being able to deal with the ionic strength of solution and being able to solve problems that involve interrelated equilibria, are essential to being able to solve kind of quote unquote real world analytical problems where most of the matrices that we encounter, we're talking about environmental chemistry, biological chemistry, the human body, municipal water, wastewater streams, are not simply composed of our analyte in deionized water. Instead, they're composed of our analyte and a host of other chemicals in the matrix that can interact with our analyte in several different ways and influence the concentration that we would observe under certain conditions, even if they don't directly undergo chemical reactions with our analytes itself. So to get an accurate picture of the chemistry going on in most of the solutions we care about, be it blood, be it fresh or salt water, be it the tap water coming out of your faucet, we have to be aware of how these interrelated chemical equilibria and ionic strength effects influence the speciation of chemicals in a specific matrix. And so this discussion that we're about to have parallels section 8, or all of chapter 8 in Harris, as well as one section of chapter 10, section 10.5. The big skills I want you to pick up for this chapter is we're going to learn how to quantitatively take into account the effect of ionic strength and how to quantitatively take into account multiple interrelated equilibria when determining the concentration of a species that participates in a particular chemical equilibrium. So we'll learn how to calculate the ionic strength of a solution. We'll talk about how we use activities of chemicals rather than concentrations to more accurately define equilibrium constants and calculate the concentration of a particular chemical species. We'll talk about how we can use the Debye-Huckel equation to calculate activity coefficients and incorporate them into a better model of an equilibrium constant expression. We'll talk about charge and mass balance equations as stoichiometric tools to solve problems with interrelated equilibria. We'll talk about how we can then take all these skills and use them to build predictive mathematical models that will define the concentration of certain species, what we call fractional composition equations and diagrams, so that we can read the concentration or the pH of an acid solution from a chart that models how even a multiprotic acid will dissociate under specific pH conditions. So we're going to introduce you to all these tools, and then we're going to show you how we can use all these tools to make mathematical models that allow us to predict the position of equilibria at a glance. Some of the big vocabulary for this term is we're going to be talking about the nature of the ionic atmosphere around ionic chemicals in solution, talk about around ions in solution. We're going to talk about calculations of ionic strength, mu. We're going to talk about the calculations of activity coefficients, abbreviated gamma. We're going to introduce charge balance and mass balance and expose you to the development of fractional composition equations, which is something that we can get from a systematic knowledge of equilibria and a simple statement, Ka or Kb, of how an acid or base reacts to donate a proton to or remove a proton from water. And so this is going to be the chapter 8 material. We'll be on this for about a week. I've listed some recommended problems from the 10th edition of Harris below here. Basically, we're going to be adding specific tools to tuck away in your toolkit for solving equilibrium problems in a variety of chemical situations. And then we're going to show you how we can go farther beyond with what we know about those tools now to build even more sophisticated tools that actually allow us to model what an equilibrium does. So this will be a bit of a demanding chapter, but I hope in the end you'll find it rewarding. We're going to start with a pretty straightforward concept in the next lecture, which is the concept of ionic strength, which will allow us to gauge the effect of spectator ions on a chemical equilibrium reaction. And I'll see you there.